some notes for you on section, let's see, this is 8.7 on numerical integration. You guys have, for years used these graphing calculators. So I'm going to pull out my TI 84 Plus Silver Edition. And I'm going to graph y equals the sine of x for starters. And I'm going to hit zoom trig because I know that's a nice choice, choice 7. So here's my good old sine function, which goes through 0, 0. Right? And actually, the first day of Calc 1, I try to explain what calculus is, and I show them two things. I show them, well, we're going to compute the slope of a tangent line by taking secant lines that get closer and closer to it. And then the other thing I usually do is I say, let's find the area under one arch of the sine curve right here, right? And so I don't show them this the first day, that their calculator can do everything I'm about to show them. But if you go down to choice 7 for second calculate, so you press second and then the trace button, it's calculate menu. And I can integrate. From where to where? Well, from 0 to what? What should my upper limit be? Pi over 2, because the sine of, or pi, right? The period is 2 pi, and then it starts repeating. But if I want to get one arch, I can go from 0 to pi. So let's do that. Second pi for the upper limit. And it even gives me a nice little picture, and it says that my area is 2. Actually, that makes for a really nice Calc 1 demo, because how do we do it in Calc 1, the first day of class? Well, we have a picture of, the graph. So let me draw the curve, which is it's drawn in blue. Okay, so it kind of goes like this, right? So here's the point pi comma 0, and there's the point. Oh, you can't see anything. Hang on. Try that again. Here's the point pi comma 0. Here's the sine curve. So you know what I do the first day of Calc 1? I don't get 2. I get answers like 1.99 eventually. But how do we do integration? It's the limit of what? An integral is the limit of a Riemann sum. That's right. And you're adding up a bunch of rectangles, really. Okay? So what's the process? This is the first day of Calc 1. What we do is we divide, A comma B into n subintervals. Okay? And what am I really doing here? I guess I'm teaching the students how to make a Riemann sum. And then there's more. How to make a Riemann sum to approximate area. So this is something you might do the first day of calculus, just to show a student what calculus is. Right? And so you divide it into how many pieces? If you were doing this the first day of class, what would you do? How many pieces would you divide it into? 5? Yeah? See, I wouldn't, because then the very first piece is pi over 5. 4 is good. 4 is a good one. Because then you can review with your students. They're supposed to know the sine of pi over 4, right? And the sine of pi over 2. Do you guys see what I'm saying? So this is the game I play. That's usually the first example. I'll do 4. Or I might do 6, right? Something that they can compute. And so then they add up the widths and the lengths, and basically you get a big sum. The width here we call delta x. And then we get the height, which is f of, looks to me like I was doing right endpoints, but it's xk star. K equals 1 to n. Here n is 4. Okay. I probably don't show all this notation the first day of class. That'll scare the crap out of them, so I don't do that. Instead, I just add up a bunch of rectangles, right? Okay, so we're going to do, well, here's what I want to do. I want to ask you, how does the calculator compute this answer to be 2? I think we do it the first day of class and we get like 1.7, and then we do it with 6 and we get 1.9. It doesn't take a limit. It doesn't do any calculus. But it does this, basically, with a bigger value of n. Because if you look at it, the calculator is very good at doing computations quickly, right? So, yeah, but what is it really doing? And that's what I want to get at, numerical integration. It turns out that there are some better things you can do than, what did I do here? Choose the right endpoint, right? Or the left endpoint. There are better things we can do. And so that's what our book gets into today, are the better things that you can do. So here's our section on numerical integration. They're going to talk about absolute and relative error. And we might get into that a little bit later. I want to get into the methods first. Then we'll talk about, you see, you want to talk about error because you want to know how far off are you. If you get 1.9, right, and the actual answer is 2, there's some error there. You could see there's going to be error because of the picture, right? There's gaps that didn't get counted. So your book starts off talking about error. They talk about the midpoint rule. And I'm just going to say quickly what that is. All that would be is this. You know, we've been choosing the right endpoint or the left endpoint. You could choose the midpoint each time. Now, one interesting thing about choosing the midpoint, if you think about it, is that then you would need to know things like, you know, so this would be pi over, 8, right? And so this gets to be a little bit tricky. So I think what I want to do is I want to come up with another example that might make things a little bit nicer, okay? So let's instead use the curve y equals the sine of pi x. How about that? Y equals the sine of pi x. And I guess what's nice about that is now the curve goes from 0 to what? Well, 0 to 2, I guess, would bring me all the way here, right? So it goes from 0 to 1. And now, I guess I'm going to divide into n subintervals. And again, you could pick whatever n you want. Maybe I'll take n is 4. Okay? So if I take 4 subintervals, let's see. Here's 1/2, here's 1/4, and here's 3/4. But what you're going to do each time, okay, is we're going to, so let's see what I have. Again, what I want is I want k equals 1 to 4, the sine of pi x xk star, where what I mean by xk star is, guys, take the midpoint times delta x, but what's my delta x going to be for each one of these rectangles? Well, you can see it's how big? 1/4, right? Okay. So we're going to have k equals 1 to 4. Well, let's not write sigma notation anymore. Let's do this. We know that the delta x is just going to be 1/4, so I'll put that at the end. And then what I should be able to do is I should be able to compute the sign of these different things, I guess. So let's see. Well, this didn't make it any nicer, but that's okay. We're going to have, let's see, one of the points I'm going to pick, the midpoint here is going to be pi over 8, right? And so I'll come up and I'll say, okay, this is my rectangle. And what's nice about using the midpoint is that you have some error on the left, too much, but you also have some error on the right, too little, right? And so I guess what you're going to have is the sine of pi over 8 plus, well, let's see, if I use the midpoint here, same thing. I'll have a rectangle which is below the curve and above the curve. Okay, so maybe I'll make that a different color. So here we select 3 pi over 8, and so we would need the sine of 3 pi over 8 times 1/4. We would also need to add the sine of 5 pi over 8 and the sine of 7 pi over 8, right? And so in theory, that's what I need to calculate. And that'll be an approximate value of the integral for y equals sine pi x. All right, so let's do some of this on the calculator. So if I go to the calculator, and go to the home screen, clear this out, I've been doing linear algebra. Here we go. So we'll do the sine of pi over 8 plus the sine of 3 pi over 8 right? Plus the sine of 5 pi over 8. Oh, too many parentheses. Plus the sine of 7 pi over 8. Let's see. So I get this, 2.61. I have to divide by 4 because we have to multiply by 1/4. And so I'm getting an approximate area of 0.653. Okay? So if we go back to what we had, this is approximately 0.653, right? Double check that. Okay, 0.6533 maybe. And let's compare to the exact area. So if I go back to the y equals screen, the thing I changed was I wanted to do sine of pi x. So I'll insert a pi here. Pi times x, right? Pi times x. Okay, so I'll graph that. So this changes the curve, and I guess what I'm going to do now is I'm going to compute the area if I integrate choice 7 from 0 to 1. What's it say? 0.6366. That's not bad, huh? Right? So you have 0.6533, whereas the calculator gives 0.6366, okay? Right? So if you want to talk about error, right, and you say, well, how far off am I? Well, we could subtract, right? So if we subtract, we have 0.0167. That's not bad. Well, what if you say we want less error than that? Then what can you do using this midpoint method? Increase n, right? We know that if we increase n, the Riemann sum will approach the value of the integral. Okay? So this is the basic idea. Now, is that what the calculator does? The answer is no. There's actually better methods. So that's what today talks about, right? So the two better methods that are mentioned in your book are the trapezoid rule and then Simpson's rule. We're going to go over both of these today. Okay? Simpson is the mathematician that the rule is named after. Now, trapezoid, could everyone draw a trapezoid for me on your paper? Go ahead and do that. So I'd like to talk about trapezoid rule a little bit. I need a new sheet. So trapezoid rule. Did anyone draw one that looks like this? I mean, that's a trapezoid. What's the definition of a trapezoid? Do you know? I mean, I always drew them this way when I drew them. You know, if my teacher had told me, I would draw that, right? Because that's a trapezoid. But what's the definition, Josh?
Is it for a four-sided shape with two sides of parallel material?
Yeah. A trapezoid, right, is a quadrilateral or a four-sided shape with, how about I say, one pair of parallel sides. I'm going to zoom out a little bit because we're not doing the best video yet. So, with this in mind, you know, the standard picture that people draw is usually this one. But the one we're going to use more often today, the parallel sides are going to be vertical on our picture. Okay? And I guess the next question I have is, do you know anything else about a trapezoid? Yeah? No? Like the formula for the area? What if I said I want you to find the area of a trapezoid? Would you guys know how to do that? No. I'll tell you the trick. You take a pen out and you draw a line from one corner to the other, making a diagonal. And now what shape is that? Well, you have two triangles, and what's the formula for area of a triangle? 1/2 base times height. As a matter of fact, a trapezoid has two bases, right? The bases are the parallel sides. And if you look, like you could find the area of this bottom triangle here, right? It's 1/2 base times height. So what you do is you think of this as B1 and you think of this as B2. And you notice that each triangle has the same height. Okay? And so the area is given by 1/2 base, well, 1/2 B1 times the height, you know? plus 1/2 b2 times the height. And so the formula that's usually given in, say, a geometry class is this one. Have you guys seen this before? 1/2 the sum of the bases times the height. That's what I need. I need that, the area of a trapezoid. Because here's the idea. Let's draw our example again. So we're going to do y equals the sine of pi x is what I said I was going to do. Okay? So we know that it goes from 0 to 1. So here's the point 1 comma 0. And again, let's just do n equals 4 again, because that makes the picture easy. Okay? So here's 1/2, and here's 1/4, and here's 3/4. Okay? And so it would be very easy to compute these points. Here, 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 and here, right? That wouldn't be hard. Okay? So I could compute the sine of pi times x for those 5 points if I wanted to. But what we're going to do, instead of doing rectangles, if you connect the points, you'll notice that you have trapezoids, right? Well, actually, this is a strange example because I actually have a couple of triangles also, which is kind of weird. Okay? But the idea is use this formula over and over again in that picture. Now, if you think about how that works, suppose I had 4 trapezoids. I don't, I get that, but it's going to take care of itself. What you could do is you could say, well, any trapezoid I have, like take this one. This is trapezoid number 2, right? So I'll call that area number 2, all right? This is 1/2 f of 1/4 plus f of 1/2. Those are the bases. And then the height is actually delta x, right? This is the height of this kind of trapezoid. Does that make sense to you guys? So that's area number 2. Now, if you have area number 3, right, you have to add that on too. Well, it's going to be 1/2. Well, maybe where should I write it? I'll write it down here. Area number 3 is going to be 1/2 of what? Well, you still have the same delta x, but you're going to have f of 1/2 plus f of what? 3/4. So that'd be area number 3. When I go to area number 4, you'll notice you have 1/2 of f of 3/4 plus f of 1 times delta x. In my example, that's just 0, so it doesn't matter. Okay? And I skipped area number 1. But these things all have something in common, right? So you can put all this together and you get the trapezoid method. It's this. The trapezoid rule really says the following. It says the area is approximately the following. So I'm going to write, let's see, this delta x, I wonder if I still want to call it that or if I should call it h. I'm going to call it h. It's the height. Well, actually, no. Let's do this. Let's show how to compute delta x. Because if you think about it, it's not hard to see that b minus a over n will give you delta x. Do you see that? In my example, what are a and b? 0 and 1. So you get 1 minus 0 over what? Do you see how delta x is always 1/4 for us? Okay? So we're going to get b minus a over n, and we're also going to get this 1/2, always. And so the trapezoid rule, the way we're going to write it is we're going to write b minus a over 2n times a really big sum. And the sum is going to be f of x0 plus 2f of x1 plus 2f of x2 plus ... I'm running out of room, but that's okay. I'll write it down here. I had a ... plus 2f of xn minus 1 plus f of xn. And what's really cool is that this is something that's pretty easy to program. You need f of x0, which for us happens to be 0. You need f of xn, which for us happens to be 0. And then everywhere else, the reason you need 2's is because like f of 1/2 appears in 2 formulas, f of 3/4 appears in 2 of the... Each other edge appears in 2 of the trapezoids. Does that make sense to you guys? And so this does it. b minus a over 2n times this stuff. Actually, I'm going to go ahead and work it out with our very simple example and see what we get. So we have, let's see, b minus a would be 1 over 2 times n. So that's going to be 1 over 8, right? Because 2n would be 8. Times... And then I think we worked out the other pieces of this, right? Because f of x0 is 0 plus 2 times, oh, now, yeah, this is nice because I'm taking the sine of pi over 4. What's pi over 4, isn't it? We get radical 2 over 2, right? Plus 2 times, oh, what's the sine of pi over 2? 1. Plus 2 times radical 2 over 2, and then plus 0. So this works out to be pretty nice. Let's write out what that is. Well, okay. Actually, the 2's cancel here and here. So I just get 2 radical 2, because I got 1 here and 1 there, plus 2 over 8. So that's radical 2 plus 1 over 4. That's not a bad approximation. Here, let me get that calculator back. And I'll compare, let's see. Here's what I got last time. I got 0.6366, right? So the actual is around 0.6366. Let's see how that compares to radical 2 plus 1 over 4. So if I go back to the home screen and I type in, let's see, square root of 2, yeah, plus 1, divided by 4, enter. 0.6036. 0.6036. Actually, if you think about that for just a minute, does it make sense that I should get an underestimate, right? So this ends up being smaller than that, right? Why? Well, because if you look at the picture, right, the trapezoids, you see the little error underneath? So you get a little bit of error. You get a little bit of error. Guys follow? Okay. I want to give you one more rule, and then I'm going to let you guys try some of this. So let's go to the book. Yeah, when they give the trapezoid rule, they kind of talk you through some of the stuff I did. Nice pictures? Let's see. Well, they're showing you that, hey, trapezoids can sometimes go above the curve. See this one? So that's good to see, that sometimes that happens. And if n gets bigger, you get closer. Okay. Yeah, the way they wrote the trapezoidal rule. Oh, I see. I don't like it as well. They put, instead of doing b minus a over 2n, they put the 1/2 inside. I kind of like the format I gave you a little better. I think it's easier to understand and easier to implement. Okay, so let's look at what they do for Simpson's rule. Yeah, here's the picture. I'm not going to go to their rectangle because I think it's a little more confusing, but I do like the discussion here. Okay? So, here, let's do this. Going back to what we've been writing down. We have this trapezoid rule, right? b minus a over 2n times this stuff. Okay? The way Simpson's rule works, I don't want to take the time right now to do the whole derivation like I did for the trapezoid rule. I just want to give you the formula, and then we'll talk a little bit about how it's derived. And if you want, actually it's interesting because you guys have projects coming up, right? If you like this stuff, you want to explore Simpson's rule, there's a project for you, okay? Deriving it and understanding it maybe a little more than you do now, okay? Actually, before spring break, I'm going to ask everybody to try and give me an idea of what project you might be interested in. I have a whole list of them on Blackboard for you. But it does. You're not limited to just what you see on Blackboard. You find a topic you're interested in, I can create a project. That just occurred to me. Simpson's rule could be a nice project. Anyways, Simpson's rule says, well, okay, see how they have delta x? Remember how we represented delta x? We did b minus a over n, right? But you notice that they're dividing by 3 for Simpson's rule? So instead of having a 1/2, you kind of have a 1/3 out front. So let's write it as area is approximately b minus a over 3n times some stuff. Now what's the stuff? F of x0 plus 2 f of x1 plus, now check this out. You see how they alternate? Oh, I had a mistake. Don't put that 2 there. You have to alternate 4s and 2s. So it's 4 f of x1 plus 2 f of x2 plus, maybe I'll keep going here, 4 f of x3 plus ... And now I'm off the screen. I got to be careful. Here we go. Okay. At the end, you're going to have, you need to end in a 4. So it's 4f of x n minus 1. And then, just like you had for the trapezoid rule, you get a single f of xn. And that is Simpson's rule. Okay? So you start off with 1, 4, 2, 4, 2, 4, 2, 4, 2, 4. It has to end in a 4 and then a 1. So I'd like to try and do it for our example. I think I have just enough room left on the paper to compare to what we got before. Let's see. If we try to implement Simpson's rule for our example, okay, b minus a, 1 minus 0 over 3 times n was 4, right? So it's going to be 1/12 times, now we have f of x 0, that was 0, plus 4 times f of x 1, that was radical 2 over 2, plus 2 times f of x 2, but that was just 1, plus 4 times radical 2 over 2, plus, and then just 0. So that we're going to compare to 0.6036 and 0.6366. And let's see what we get. Oh, actually, we could simplify, right? This is 1/12 of what? Isn't it? Well, you have 2 radical 2 here, another 2 radical 2 there. So you have 4 radical 2 plus 2, right, guys? Okay, so we want to get a decimal. Well, 4 radical 2 plus 2 over 12. So if I go back to the calculator, well, I'm just going to do second entry. I almost have that written. 4 radical 2 plus 2 over 12, that's the same as 2 radical 2 plus 1 over 6. Let me insert a 2 here. 2 radical 2 plus 1 over 6, and let's see how close we come to the answer. Ah, check that out. That's closer, isn't it? We got 0.6380, and that's pretty close to the actual 0.6366. This one's actually a little bit over 0.6380. It's, you know, it's accurate to 2 decimal places and almost accurate to 3 decimal places. And this is only with 4, n equals 4, okay? By the way, you can't do n equals 6 for Simpson's rule, okay? You need to have, well, I guess you could do 6. You can't do 5. N must be even for this to work for Simpson's rule. You know, one problem with Simpson's rule right now is that it seems like magic, maybe, right? It's not. But I didn't derive it. But I'm going to show you that we can do other things too. So let's take a look at the book and maybe pick out a problem and try it. Okay. So applications. Period of a pendulum, arc length of an ellipse. Yeah, these are all cool, but let's just do one of the homework problems. I only assigned through like the 30s for you guys, so. Well, okay, 14 and 18 is kind of nice, right? It says, find the indicated trapezoid rule approximations to the following integrals. You're going to compare it to midpoint. But I really want to look at Simpson's. Where's Simpson's? Here we go. Trapezoid rule and Simpson's rule. Okay. So let's do number 34. Number 34. We want to integrate from 0 to pi over 4. Hey, by the way, is 34 one that you guys know how to do? We could actually get the exact answer? how would you do number 34? Okay, what's the trig substitution? Arctangent, yep. But actually, if you work it out, the whole thing works out and you end up getting theta is what you, or d theta is what you end up integrating, which becomes theta, so you just get inverse tangent. I mean, this answer, I can just tell you right now, if I wanted to do it by hand, this is the arctan of x from 0 to pi over 4. And so do you guys know the arctan of pi over 4 or the arctan of 0? Well, I know the arctan of 0 is 0, but I certainly don't know the arctan of pi over 4. That's weird. I know the tangent of pi over 4. The tangent of pi, I wonder why they did this. It's funny, if I were writing this problem, I would have put a radical 2 over 2 here. I mean a 1 here, and then you'd get pi over 4. That's weird. All right, well, it is what it is. So you get the arctan of pi over 4. All right, so here I go, guys. Instead of punching all of it in the calculator, I have a nice link I'm going to share with you guys for the homework. This is Desmos, okay? And what it's doing here is it's actually performing Simpson's rule, okay? So you're going to get to play with this to do the homework, I think. But if we want to do this, it's really nice. You could set a and b to whatever you want. You could type in whatever function you want. So I'll tell you what, I'm going to go up here and change the function. Let's see. So what function do we want? We want 1 over 1 plus x squared. I feel like if you're going to do numerical integration, you ought to use a computer, right? Okay. Ooh, where's my function? Well, I guess you just can't see it. There it is. Okay, so 1 over 1 plus x squared. Yeah, that's zoomed out too much. Well, that's because these are kind of like 50. Yeah, we don't want it that... Got to figure out how to stretch that a little better. Oh, yeah. Good thing I have a touch screen. Okay. There we go. Okay. And now we're going to change A and B. We want to go from 0 to, what'd they say? They said pi over 4? All right, well, I'll type it in. Pi over 4. That was weird. All right. So this is the region I want. And to be very accurate, you can make n equal to 28. What'd they say they want n to equal? 64? All right, let's see if I can turn it up a notch. There we go. That's going to be pretty accurate. I mean, is there error at all? Here, let's zoom in and take a look. Yeah. I mean, one thing is, though, I'm not sure you really know yet what it's doing, so let me say a little bit about that. I'll pause. The way that Simpson's rule works is kind of like the trapezoid rule, but instead of using consecutive endpoints, it actually uses 3 endpoints in a row. And what it's really doing, it's fitting a... Because if you think about... Here, let me show you. Back to our picture. You know, we have this curve, right? And at any particular place, the trapezoid rule, the way it works is it's replacing the curve with straight lines, right? So there are 2 straight lines. And so I guess in this picture, the trapezoid rule is going to give me an overestimate a little bit. Are you with me? So trapezoid rule uses straight lines. Simpson's rule, what it's really doing, it's using parabolas. So I think that's kind of interesting. But if you just had 2 points, do you guys realize there's infinitely many parabolas that go through those 2 points? Right? You could have really big ones or you could have really small ones, right? But if you give it 3 points, it turns out there's one uniquely defined parabola that goes through there. And that's what Simpson's rule uses as the upper piece of its border. And the parabola will actually be more accurate than the lines will, in most cases. Does that make sense to people? There's going to be less error. So, anyways, this goes through the calculation. And, I mentioned the project. If you enjoy programming, take a look at this Desmos sheet when you are working on the homework. There's a lot of cool things going on. This is just where am I, and it's going to show the picture. This you guys should be comfortable with, b minus a over n, right? That's my h. And then what it's doing here is it's adding up some different areas. Oh, and then down below, it gives the trapezoidal rule, okay? But anyways, right here, this is Simpson's rule, right? Notice that you have some 4s and you have some 2s and you have the h over 3, okay? So my Simpson's rule approximation for number 34 was 0.6658. Let's see, 0.6658. I'm going to write that down for Simpson's. And I guess what I want to do is I want to compare Simpson's rule to the arctangent, right? So Simpson's rule gave me this 0.6658. We never actually finished. What's the arctan of pi over 4? You want to compute that? You're going to make me do it. All right. Inverse tangent of pi over 4. Look at that. 0.6657. So the exact answer is 0.6657. Well, if you round, it's 0.6658, right? Hey, let me check that. Maybe, yeah, 0.66577,375. Let me compare that to what we have here. 0.6657737. Wow, we're really close. Of course, that's a big value of n, right? That's n equals 30 or 64. Let's compare that to the trapezoid rule. Oh, by the way, yeah, see parabola, points, and curve. This is kind of behind the scenes showing you how Simpson's rule works. But here, they work out the trapezoid rule, 0.665766. So, yeah, they're all pretty close by the time you have that many. But I'm hoping that if I put this link on Blackboard, this will kind of give you what you need for doing the homework.